Good morning. For today's video lecture, we're going to be talking about kinetics and rigid body translational systems. So, Newton's second law and kinetics. So in kinetics, we are going to build directly on Newton's second law, which is F equals ma. So force equals mass times acceleration. In rigid body kinetics, we can additionally add the rotational version of Newton's second law, which is m equals I alpha. So that is the moment, the mass moment of inertia, and angular acceleration. So if we put known forces, moments, masses, and mass moments of inertia into the above equations, for any given object or any given body, we're going to have the equations of motion for that object. So these are similar to the equilibrium equations that we had in statics, except they are now equations of motion because they do not sum up to be equal to zero. So by solving these equations, we can either find forces and moments given accelerations, or you can find accelerations given forces and moments. So with translational systems, which is what we're talking about here, we have an object that is going to have translational, so we're going to have linear accelerations, but zero angular acceleration. So this is going to be a good starting point for our systems. So in that case, we can, in a 2D system, we can break our force into x and y components. So sum of forces in the x equals mass times acceleration in the x. Sum of forces in the y is equal to mass times acceleration in the y. And the sum of moments about the center of mass is going to be equal to 0. So in kinetics problems, it is important, so rigid body kinetics problems, it's important that the accelerations are all about the center of mass. So when I say ax, I'm talking about the acceleration of that center of mass point. When I talk about ay, I'm talking about the acceleration of that center of mass point. And my moments all need to be about the center of mass. It's summing the moments about other points are not going to work as they did in statics. All right, so with a translational system, despite the sum of the moments being equal to 0, like we had in a statics problem, the forces are often quite different from a statics problem. So an example of this is a car under heavy braking, where the normal forces shift in order to balance the moment that the friction forces exert about the center of mass. So when you're in a car, if it is either sitting still or kind of rolling along at a steady speed, you're going to have those two normal forces, and that's really it. As soon as you apply the brakes, you've added an extra force in there. That force, since the friction force is down here at the ground, it's going to exert a moment about the center of mass, which is going to be somewhere up in the middle of the car. So when you do that, you need to kind of adjust your moments, or adjust the normal forces. So you're going to have more normal force up front, less in the back. That's why your car tilts forward, in order to keep the sum of the moments being equal to 0. All right, so solving a rigid body kinetics problem, the process for this in general, it's going to be very similar to what we used in statics. So number one, you always want to set up your free body diagram, draw the body separated from its surroundings, draw in all of the known and unknown forces. I use red for those forces personally, as well as key dimensions and angles. And so I use blue for the key dimensions and angles. You also want to draw in the acceleration vector. I personally use a blue dashed vector for my acceleration. So once you've got your free body diagram with the forces, the dimensions, and the acceleration all drawn in, you're going to use that free body diagram to write out your equations of motion. So remember, sum of forces in the x is equal to mass times acceleration in the x. Sum of forces in the y is equal to mass times acceleration in the y. And for a translational system, the sum of moments about the center of mass must be equal to 0. All right, so these may be supplemented with kinematics equations if you need to relate acceleration in the x and acceleration in the y. You might need to add some other kinematic stuff in there, but come up with at least as many equations as you have unknowns to make it a solvable set of equations. Last step, once you have your equations, you're going to solve for any unknowns that you have in those problems. So that's the last slide we've got for today. Thank you for watching, and I hope to see you again.